All right, hello. Hope you're doing well. In this video, we're going to talk about one of probably the more confusing and difficult concepts with bonding and geometries, which is planarity. Can atoms be in the same plane? This is one example problem, and we'll point out kind of how this can work with these kinds of models that I can show you because they tend to help to visualize. And one thing I'll first start with is just which geometries are planar. So this would be a good idea just to know. You have things like linear, bent, which might be something like this, trigonoplanar. Obviously, it's in the name, it's planar. T-shaped and square planar, obviously. Those would be the 5 geometries where all the atoms are in the same plane. And when you're looking at a molecule in a problem, sometimes the problem can be worded differently. So what I would also mention in the beginning here is sometimes it is a question like this, which is, the atoms must be in the same plane always versus can be in the same plane. And so in some cases it's different. It wouldn't really be different for this question, but when you're looking at a molecule, what you want to kind of keep in mind is the rotation of bonds. Rotation of bonds. So by that I mean that if you have a single bond, which is just a sigma bond, remember, that can rotate, and it is rotating all the time. So sometimes by nature of rotating and spinning, you can line the atoms up to be in the same plane, and then they aren't in the same plane. So that would be when you have a case where it could be different. Double bond or triple bond does not rotate, and this model here is kind of showing a double bond with a pi bond system, and that, remember, does not rotate at all. So that locks the atoms in the same plane always. So that's what we'll talk about also with this problem. Okay, so we'll jump right in. This one, we have C3H4 with 2 ways of drawing it. So the first way I'm going to draw it is with a triple bond and a single bond. And then we'd have basically this structure. Okay, so in this structure and kind of in these problems, my method is usually to take a central atom like carbon and say, okay, what's the geometry, right? So around that atom, you should have 2 bonded atoms, no lone pairs. That's linear. That is planar, right? So right now we have, just if I'm kind of thinking about which atoms would be in the same plane, we have those 3 definitely in the same plane. We also have this second carbon, the middle carbon, being linear. So now we extended the plane to all 3 carbons. So all 3 carbons and the hydrogen on the left are in the same plane. They're in the same line, actually, which is definitely the same plane. And then we get to this carbon on the right, which is tetrahedral, right? So this is where, again, we want to be able to easily identify the geometry of a central atom, which is not a planar geometry, right? So what we have in a model, maybe I'll stop the share to make this bigger. So we have the hydrogen, triple bonded carbon, and carbon that's tetrahedral. So obviously these hydrogens are breaking the plane, 3-dimensional, and therefore all 7 atoms are not in the same plane, and they could never be in the same plane even with rotation. Okay, so no, so for this one it would be atoms no, atoms not in same plane. All right. So, and again, when you get to one of those geometries that's not planar, like tetrahedral or pyramidal, for example, those are all three-dimensional. Oftentimes, too, if you were to see a depiction of a tetrahedral atom or maybe a pyramidal atom, you have like the dashes and wedges. So that the dashes and wedges are good, indications that they're not two-dimensional because they're popping out or going into the paper or the screen or whatever. So if you just had kind of regular lines like this, that could be all planar, right? Whereas this notation is three-dimensional and not planar. So just, again, something that you can start to kind of notice and file away. Okay, so other way of drawing it is, and this is good practice also to try and draw these two different structures for it, is with two double bonds. So we have this molecule here, and this one is where it gets tricky, because if we go through the geometries, this is trigonal planar. We have 3 bonded atoms, no lone pairs. And so again, this means that all 4 of these atoms are in the same plane, right? If you have a trigonal planar geometry, they're all in the same plane. And then we have linear in the center, which again is in the same plane. So now we have the plane, including these 3 carbons. And then we also would have a trigonal planar over here. So we could, and then envision, oh, this is all in the same plane. Therefore, it's like if A equals B, B equals C, then A equals C. So if they're all sharing planes, this looks like it's all planar. But it's not. So this is the trick. But atoms are not all in the same plane. Okay, so how do we know? This is where it gets into the orbital picture of the bonds, and where we actually need to break down the hybridization and how the bonds are being formed, specifically the pi bonds. Okay, so we have left carbon, sp2, right carbon, sp2 as well, center carbon, sp. This is something that we did in the last video, and you should be able to do again by looking at the electron regions around each atom and then assigning the hybridization. So with sp2 hybridized atoms, if you remember, they are usually involved in one pi bond because they have one leftover p orbital. So this carbon on the left would have essentially, I'll just kind of draw these hydrogens like this. These are going to be sigma bonds, right? So if you were to kind of, again, think about them, they're always like in the plane. They're just in between the 2 atoms. There would be another sigma bond. Maybe I'll make this orange. Another sigma bond between that and then the middle carbon, right? Okay, so, and then also there would be a sigma bond between these middle carbon and the right carbon, those ones, and then also between the atoms on the right. But the key is with these atoms on the right, they're going to have to be in a plane that's perpendicular to the atoms of hydrogen on the left. And the reason this is, so these are again the sigma bonds here, is that if you remember, when you have sp2 hybridization, we have one leftover p orbital. So if this is a pi bond here, if I look at this carbon here, the p orbital that's left over, let's say I draw it up and down. So this is our p orbital that's left over, right? And that's going to bond to the carbon in the middle and form a pi bond. So this carbon in the middle then is going to have to also use a vertical p orbital, and then these two, when they overlap, right, that's the pi bond. That's one pi bond, remember. So one pi bond has two areas of electron density, above and below the bond axis. So that carbon in the middle, and maybe I'll just kind of say this has one p orbital, kind of unhybridized. This one also has one unhybridized p orbital. But the carbon in the middle, when you have sp hybridization, remember that you take one s and one p orbital and mix them together. So that one in the middle is actually going to have two p orbitals left over, right? So that one in the middle that has the sp hybridized, having the two leftover p orbitals that we didn't mix together to make hybrid orbitals, how are those p orbitals related? Well, they have to be perpendicular because by nature they're always perpendicular, like x, y, z. So if this green one in the middle is vertical, like call it x or whatever, y, then the other one has to be the other way, which is going to be, in this case, coming out of the screen and going into it. So this is going to be our p orbital on the center that's perpendicular. Again, if we think about like giving them like green is px, red is py, or whatever. And then on the left carbon, in order to form that pi bond, it has to use the same kind of direction of p orbital. So these are overlapping in this way, right, to make the pi bond on the left. What that could look like in these models is this. Maybe this might make it a little bigger to see. So the left carbon has, a horizontal pi bond, and the right carbon and the middle one have a vertical pi bond. So that means that these hydrogens over here are in a plane that's perpendicular to these, right? There's a twist in the molecule of 90 degrees. So that rotation around the middle of 90 degrees is really difficult to notice unless you actually were to draw the bonding like we do here. And so this is a kind of high level question. But the answer, again, I mentioned, is that the atoms are not in the same plane. The hydrogens, so not all in the same plane, due to the kind of the back-to-back pi bonding would be the answer, or the reason for the answer. So the two H's on the left are in a perpendicular plane to the two H's on the right. And so hopefully that makes sense. I know it's probably difficult. Pretty much the hardest problem you could get with the planar. So keep that in mind. And I think just doing some practice problems like always is a good way to try to learn these concepts and practice with various examples and see if you can tell. And feel free to email me if you come across something like a book problem. I can draw it out on here, send you an email, or I can even make another video and post it to Gaucho Space if it is something that I think will be helpful for everyone. So good luck with the studying, and I'll talk to you later.